Hi, welcome to another video. In this video, we're going to talk about how we can go from x-intercepts or zeros or roots into a polynomial type function. So it's pretty important because what we're going to be learning at the very end of it is that if we have a graph and we can identify some x-intercepts, well, then we can build a function from it. Same thing's going to happen in the next few videos where we find some zeros and then build functions from that as well. So pretty useful for graphing, gives us a very good impression of, or interpretation, I should say, about how x-intercepts and polynomials play together. And one way we can go is from x-intercepts into the polynomials. So we're going to learn how to do that. And how we're going to start is we're going to kind of rediscover how factoring and the zero product property give us x-intercepts, and then we're just going to go backwards from that. So here's what we're going to learn. We're going to learn that if you have an x-intercept, you can create a factor. And by using the zero product property, we can take those factors and build a polynomial from it. So this is only to do with polynomials for now, but we can use some of the same ideas to build rational functions later on when we get to rationals, which is a polynomial divided by another polynomial. So let's check it out. Imagine we have a function x squared plus 2x minus 8. And I know that you've seen this before, but remember what I'm trying to teach you. I'm trying to teach you how going from here to our zeros, our x-intercepts, our roots, if we go backwards, we're going to be able to start with zeros, x-intercepts, or roots and find polynomials from that. So let's discover it. How we find a zero or an x-intercept or a root of any function is we set it equal to 0. So let's start that. Now, if we don't have factoring available to us, for quadratics, it's pretty nice because we can just do the quadratic formula and we're good. For cubics, those power 3s, there is a way to do that. There's a formula sort of that you can use, and even fourth powers you can do it. It's very, very labor intensive. For fifth power and higher, degree 5 polynomials and higher, there is no general way to factor it. That means there's no formula that you can just throw at it, plug in the coefficients, and it does it for you. Quadratic formula is the easiest one that we have. There is one for power 3 and a power 4, but none for a power 5 and higher. You can prove it, but it takes some fairly high level math to do it. You learn this in like a bachelor's level mathematics. And so we're not going to be doing that. Maybe even master's level. I can't remember where I learned that. But we're not going to be learning that. What we're going to be learning a little bit later is if you have a power 3, power 4, power 5, power 6, if you can find some zeros, that means you can factor it. And so you're going to be learning that in the next few videos. What that means is that factoring is sort of our best case scenario for working with these polynomials. For quadratics, man, we should really try to factor them, and this one is in fact factorable. But later on, if they're not factorable, we're going to be trying to find x-intercepts so as to make them factorable. I'll teach you about the rational zeros theorem a little bit later. So let's go ahead and factor this. This, of course, we know is x plus 4 times x minus 2 equals 0. Now here's the point. Because we were able to factor this polynomial, we're able to use the zero product property to set each of those factors equal to 0, and it's going to give us 2, in this case, real x-intercepts. Now keep in mind, I know that you know this. What I'm going to do is, after we finish this, I'm going to structure this problem as a way to go backwards and get a polynomial from your x-intercepts. So zero product property, and if we solve that, we get 2 x-intercepts. These are the places where this parabola, upward opening, crosses or intersects the x-axis at -4, 0 and at 2, 0. Now here's the point. What if you were only given this? Say, hey, we know 2 x-intercepts. Can you go backwards and figure out the function from it? And the answer is yeah, and it's pretty easy. There's only a couple things that we want to make sure that we do. Number one is we want to make sure that we have any multiplicity taken care of with an appropriate exponent on the factors that we create from our x-intercepts. We also want to make sure that we match degrees. That's the degree of the polynomial if one's given to us. Lastly, if we have a point that's given, and we get this oftentimes from graphs. We're going to do this in the last half of the video. If you have a point that's given, you can find a specific polynomial. If you don't, then you find a general polynomial, sort of a family of curves that has these x-intercepts. And we'll talk about that as we get into the factoring. We'll notice that, man, this could be a whole lot of different polynomials that are given. So typically we have a little a out front to say this is a family of polynomials of a specific, that has specific x-intercepts that would fit this. And so we'll talk about that as we go. So let's go ahead and let's start going backwards. So what if you were given some x-intercepts? Can you go back and find a polynomial? Well, let's suppose that we have x-intercepts of -3, 4, 1, and 0. What we're going to do is we're going to allow the zero product property to work for us in reverse. Model it exactly the same, just going backwards. So if we have x-intercepts, then we know that x would equal -3, x would equal 4, x would equal 1, and x would equal 0 for some polynomial. If that's the case, if that's true, if x equals -4, well, then that's an x-intercept of some function. We're saying the reverse now. Here's your x-intercepts of some function. That means that x equals -3 for some function. We're going to find now x equals 4 for some function, x equals 1 for some function, and x equals 0 for some function that we're going to find. Those are the x-intercepts. Now, how do we build a factor from it? If you solve this so that you get 0 on one side, so basically undoing your solving, if you add 3 to both sides, or subtract 4, subtract 1, subtract 0, don't do anything, then that right there gives you your factors. We're basically doing the opposite of this step. You're saying, hey, you know what? From x plus 4 equals 0, I got x equals -4. Can I create these factors? See, here's the point. What we want is we want to find the factors so that every factor is set equal to 0. If we do that, the zero product property works both ways. It says if you have products that are multiplied to 0, then every factor can be set equal to 0. But likewise, if you have factors set equal to 0, you can multiply them together and that product is still equal to 0. That's the zero product property in reverse. So we say, all right, here's our x-intercepts, great. Let's create some factors where the zero product property is going to work. In other words, have some factors set equal to 0 and make sure that every single one of those factors is equal to 0. Then what this says is, man, you have 1, 2, 3, 4 factors. Every one of those is coming from an x-intercept. What that means is that you can develop a polynomial, not the only one, but a polynomial that has these as its factors. And by setting them equal to 0, you can use the zero product property in reverse. And so we're going to do that right now. We're going to say, all right, these factors are x plus 3, x minus 4, x minus 1, and x. We typically put individual term factors in the front of an expression, not out of necessity, just out of convenience. It looks a little better. We don't lose them as often. So let's check it out. And just think through it with me. If you were to do this backwards, if you were to have a function like this, a polynomial that's been factored like this, and you have it equal to 0, you could certainly say, well, yeah, by the zero product property, it'd have x equals 0, x plus 3 equals 0, x minus 4 equals 0, and x minus 1 equals 0, and that would give me these 4 x-intercepts. So we're basically just doing this in reverse. That's really all there is to it. It's not super complicated. You just need to know what to do. And this is one way that we can go from x-intercepts into a factored version of a polynomial. Now, you'll notice something about this. This right here is a function that's set equal to 0. To get a function out of it, you just go, yeah, one function that would have these x-intercepts could be f of x equals x, x plus 3, x minus 4, and x minus 1. Now I said this is a polynomial that would have these x-intercepts, and I don't want to just have your brains explode or anything, but you can put any number out front and have the exact same x-intercepts. You go, wait a minute, what? Any constant factor, like let's say 7. If I put 7 there, that 7 has absolutely nothing to do with those x-intercepts. It wouldn't change it. Or -7, it still would not change those x-intercepts. Try it if you want to. If you put a -7 in front, you would still set x equal to 0. The -7 does nothing. Even if you take the -7 and put it over here and divide by -7, it does nothing as far as your x-intercepts. All that would do is start changing the let's call it dramaticity, the dramaticness. I think I just made up 2 words right there, of how it grows between the x-intercepts, or shrinks, or reflects. It would certainly change the shape of your graph. Absolutely. And the end behavior of your graph. Yeah, negative to positive for sure. But it would not change the x-intercepts, the way that this graph interacts with the x-axis. Now that's interesting. What that means is that when you do this technique, if you do not have a specific point off of the x-axis that you're going through, then you are not really sure about a specific function itself. And to signify that, we usually put a little a in front to say, you know what, any a that's a constant factor, any a, positive or negative, would not change the x-intercepts. So any a here would have exactly the same 4 x-intercepts. Now that's really interesting. So without a specific point, I said that twice now, without a specific point, then you leave this a here because you're now talking about a family of functions that all have the same 4 x-intercepts. Now, what if you do have a point off of the x-axis? Well, then you can use it. I'm going to explore that when we get to the graphs. We'll see the point, or if they give you a point like, hey, this goes through the point 1 comma something, then you can, like 1 comma 2. Well, then you can plug in the 2 for your function, the 1 for your x, because this is the input, that's the output. Input is 1 for your x's. Output would be 2 for your f of x, and you can use that to solve for a. It's not all that bad. But without that, without a point that is off of the x-axis, you cannot get a specific function. I hope that you understand that. Now, why off the x-axis? Well, because anything off of the x-axis is not going to be an x-intercept. The zero product property says that you're multiplying to get 0, so each of those individual factors doesn't really matter if one of them is 0. It's something off of the x-axis does matter, and it won't be 0. It will affect the shape of your graph, and that one point will kind of dictate what the shape of the graph is. It'll allow you to solve for that a without becoming 0. So we're going to explore that in graphs. And that's about all there is to it. One thing I do want to tell you is that sometimes you'll be required to distribute this. I generally don't, because it takes a whole long time. If you're required to, here's how to do it. Start at the right-hand side. This is my opinion. I think it's the easiest way to go. Start at the right-hand side, and you would FOIL this or distribute this. Then once you have this expression, distribute the x plus 3, and then distribute the x, and then distribute the a if you have to. Typically, you'll want that to be a number if you're going to distribute that. So hopefully you have a point that's off of that x-axis. And that's really all there is. So we're going to keep on going. We'll have a couple more examples where I show you how to deal with multiplicity and why they give you a degree here, because that can be confusing. Like, who cares? Like, you didn't give me a degree here. Why does that matter? I'm going to explain that as we go through this, and I'll show you why this was sort of an incomplete question to begin with. So let's go ahead. Let's say they give you some zeros, or they can call these things roots, or they can call these x-intercepts, as long as they're real x-intercepts. When we start getting into complex zeros, complex roots, you wouldn't call them x-intercepts anymore because they don't intersect the x-axis. When they give you these zeros, what we can do first off is to understand that zeros are, if they're real, are where your graph intersects the x-axis. That means that we would get x equals, man, I talked so long my pen ran out of ink. Goodness, guess I'm used to that. We would get x equals -1, and we would get x equals 0, and x equals 4, and x equals 9. If those are zeros, then that's where the graph would intersect the x-axis. And we've done this many times in reverse, where we have a function, we factor it, we use zero product property, and we get our solutions here. You could also do -1, 0, 0, 0, 4, 0, -9, 0, but it doesn't really make a difference. From these x-intercepts, or these real zeros, we can create factors. So we're being smart about it. We're understanding that if I get 0 on one side of my equation, basically going opposite of solving. So in this case, adding 1, doing nothing, subtracting 4 and adding 9. Then what this allows us to do is to view these x-intercepts as some result of a factor that's set equal to 0 by the zero product property. We're straight up going in reverse of this. Well, now, if all of these are set equal to 0, we can consider them to be factors of some polynomial, some function. So we'd say, all right, well, one factor equal to 0 is x plus 1. This is what gave us the x-intercept of -1 in the first place. And x, we usually put individual term factors out front. And x minus 4, and x plus 9. Those would be the 4 factors that we would get from these 4 x-intercepts. You're done. The only thing that we have to do right now is to say, by the zero product property, this is true. We're using it in reverse. So we start with x-intercepts, we say, let's create some factors that are set equal to 0. Then we have all of our factors set equal to 0. They have to come from somewhere, or you could create a function that uses the zero product property to state that those are factors. So we write them all out. The last thing that you would do is you'd say, because I have not given a specific point here, this is one of many functions that would satisfy these 4 real zeros. And so we'd say, yeah, there's a function that's possible. This is one of them. We don't want to leave it here equal to 0 because we're asking for a function. Technically, we're asking for a polynomial, and polynomials are typically not factored when you write them in standard form. And so you would usually distribute this. So distribute these two, and then this one on top of it, and then this one on top of that. And then if there's a coefficient out front, then you distribute that as well. For us, we say this is one of many possible. So give it a little a, because whatever constant factor you put out there, it would have the same exact x-intercepts, for sure. So that's about as far as I would require it to go. Again, you'd have to distribute if you want a polynomial. Now, the degree 4, what does that mean and why is it relevant? The degree 4 actually saves you work. Here's the point of doing this. What we want is if you have a degree 4, then you should have at most 4 factors. 1, 2, 3, 4. 4 factors that have variables. Any more than that, and you would have a degree that's higher than 4. So imagine, remember our fake distribution? I hope you remember what we did in the last 2 videos. If you were to distribute this, you would take x, 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 and x. That's x to the 4th power. That matches our degree. What it does is it prevents you from doing things like this. It prevents you from putting in some factors that are irreducible quadratics and wouldn't give you any more x-intercepts. You go, what in the world does that mean? For instance, if I allowed this to be anything but a degree 4, if I said, let's make it a degree, I don't care. Well, I could start tacking on some irreducible quadratics. Like x squared plus 9. X squared plus 9, hopefully it doesn't come as a shock to you, is not factorable. That's not x squared minus 9. It's not a difference of squares. It's called an irreducible quadratic, which means you cannot factor it any further than that over the real number system. Now, we allow complex numbers, sure, but we're not talking about that yet. We can't factor it. It's not going to give us any more x-intercepts. You can try all you want. You go, how's that factor? Well, x plus 3i and x minus 3i. Is 3i an x-intercept? No, it's not. Is it a 0? Yes, but it's a complex 0. So it's not what we're talking about here in terms of the real number system. That's not really allowed as far as graphing on our x-axis the way we're normally used to. So what would that do? This function would have these as its only 4 real x-intercepts. This would do it. But notice why the degree 4 is there. If I allowed that, that would be now a degree 1, 2, 3, 4, 5, 6. That would be a degree 6. Do the fake distribution in your head right now. Make sure that I'm right. You take x, 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 and x squared. That would be a degree 6 polynomial once you're done. Well, that's not what we asked for. That's a degree 4. So if we didn't have that statement of a degree 4, you'd be allowed to multiply as factors these irreducible quadratics that wouldn't give you any other x-intercepts, and you could do it all day long. X squared plus 5, and keep on going. X squared, whatever doesn't factor. And you would have these degree however much you wanted that would still only have 4 x-intercepts. That's what the degree 4 is there for, is to make sure that you're not degree 4 is there for, and make sure you're not doing too much work and adding things in there that that wouldn't change your x-intercepts, but would certainly be much more complicated of a graph. Which is why this one I told you was a little bit incomplete of a problem. You see, this says, suppose we have x-intercepts of just these 4. Well, this would be a function, but I could also put on some irreducible quadratics and not be wrong. There's many different answers to that. Any constant would make a function with those x-intercepts. Any irreducible quadratic would not make any additional or alter those x-intercepts. This x squared plus 9 does not change the fact that we only have 1, 2, 3, 4 x-intercepts. It would change the look of your graph for sure. So would the coefficient of any sort of constant. It would change the look of your graph for sure, but it would not change the x-intercepts. So that's really the whole rundown. Start with your x-intercepts, make some factors equal to 0, make them factors using the zero product property in reverse, call it a function, and you're done. Just don't overwork. So if you have a degree 4, you should have at most 4 factors. That's about it. You can't have less than that, but I'll show you how the degrees should match up. So we do our work, we sort of do our fake distribution to make sure that we're right. Here's 1, 2, 3, 4 x's, that's a degree 4, so 4 factors with x to the first power in each one, and we know that we're right. Put a little a out front, and you're good to go. All right, let's move on to the next couple. So we have some multiplicity up here. Are they any harder? No, they're really not. I just want to show you what to do with the multiplicity and how that works into the powers of our factors. So we're going in reverse. We say, hey, this really only has 2 distinct x-intercepts. We would have x equal 1 and x equals 2. All right, that says here's our zeros, x equals 1 and x equals 2. What about the multiplicity? We deal with that later, and then we check our degree. So what we're going to do is we're going to say every time we have an x-intercept, it should come from some factor. We find that factor by setting our one side equal to 0. And that says, hey, if that's true, then this came from something by the zero product property. That'd be x minus 1 would be a factor, and x minus 2 would be a factor of some polynomial set equal to 0. And that's great. It says, here's our x-intercepts, cool. Subtract 1 and subtract 2. This would be a factor, and this would be a factor. That's where our x-intercepts would have to come from. Now is where we deal with the multiplicity. If you remember from, I don't know, this last video or one before that, we talked about multiplicity as the power of the factor from where we got our x-intercept. So if these are x-intercepts, they came from some factor. That factor has an exponent to it. It's either 1 or 2 or 3. It's not 0 because then we wouldn't have that factor, but it's some sort of integer. Remember, polynomials can't be fractions or negatives. Some sort of positive whole number, integer. Typically, possibly including 0, but we're never going to see that. So our multiplicity basically tells us how many times that factor is repeated. And so we just have to read it. So here's our x equals 1. Cool. We built a factor from it, and now we're going to look at our multiplicity. This says this factor has a multiplicity of 1. It's not repeated more than one time. So you have this, you could put a 1 there. We're not going to, but that's where that number is coming from. Now, x minus 2, it says here's our x-intercept, here's our factor, and it said x equals 2 has a multiplicity 2. That means that it was repeated. It was a repeated 0, repeated root, repeated x-intercept. That means it had to have a power 2 there. That multiplicity 2 is the exponent of the factor from where you got your x-intercept. So going in reverse, you have your x-intercept, build your factor, and then put the multiplicity on after the fact. Now, that's our polynomial as long as we write this in function form. This is one of many polynomials that has these as x-intercepts with the appropriate multiplicity, the appropriate repeatedness of those roots. You see, if we took this and said, hey, x minus 1 equals 0, cool. X minus 2 equals 0, you'd have another one, x minus 2 and x minus 2. That's a repeated root, and that's where the multiplicity is coming from. That's what that's saying to you, is that that 0 has been repeated. Now, I also mentioned something that your degree is something you'll want to check. So this should be a degree 3. This should have at most 3 factors. Now this only has 2, sort of. It has 1 and it has 1 that is repeated. That really counts as 3, doesn't it? So x minus 1, x minus 2, and x minus 2. That's 3 factors, 3 linear factors. You will have at most the degree number of factors. If you have irreducible quadratics, you'll have less than that. We're going to get into that in several more videos, where if you allow complex numbers, you'll have exactly the same number of factors as your degree. If you have complex numbers that you're working on and you factor, you'll have the same number of factors as your degree. You'll have at most the degree number of factors if you're working over reals. Those irreducible quadratics sort of mess that up a little bit. So we're going to fake distribute. We're going to make sure that we match our degree. We're going to put a little a out front to represent this is like a family of curves. So if we check it out, we'd say, hey, this factor would give us x. And if we fake distribute, the biggest power we get out of this would be x squared. Hey, x to the first times x to the second is x to the third. That would be our leading term that matches our degree and that we know that that's correct. The only last thing we're going to do is say that any coefficient that, those are technically constants anyway, if it does, as long as it doesn't have a variable in it, that's not going to affect those x-intercepts one bit. So the last one, let's go ahead and work through this real quick. You probably should try this on your own. One thing that you can do, just really quickly, this typically works pretty well, look at your degree and count up your multiplicities, and they should usually match up. The only time they wouldn't is if you have a hidden degree in there, or they're not giving you multiplicity. So then you'd want to match your factors to that degree. So if you have an irreducible quadratic, that can mess it up, but usually you don't see that. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, hey, my multiplicity matches my degree. That's great. That's really what we're looking for. Then what we're going to do is we're going to take all of our x-intercepts that they've given us. Be careful here. Sometimes we go too fast and we go, oh yeah, x equals -2, and we see the 1, and we go x equals 1. Just make sure that you're setting your x equal to the x-intercept and not accidentally the multiplicity. It happens. Okay, so I'm going to double check. X equals -2, got it. X equals 5, got it. X equals 0, got it. And x equals +1/2. Got it. So I'm not worried about the multiplicity right now. That comes as the factor, as the power of the factor we're about to create. So we're going to make sure that we have 0 on the right-hand side of all of these 4 equations. I need to talk about this one in just a minute. So let's see, x plus 2, cool, we added 2, x minus 5, subtracted 5, x equals 0 is good, and x equals -1/2 equals 0. These right here are the 4 factors of a polynomial that would have these x-intercepts. We're going to use the multiplicity to make sure that we have the same degree. It's given it to us, we just won't need to use it appropriately. So we're going to go ahead and we're going to write this out. I'm going to put the x first. It really doesn't matter the order. But by using the zero product property, we're saying these factors are all equal to 0. Therefore, if I multiply them together, that product would still be equal to 0. And this is one function that if I were to set it equal to 0, that's how we find x-intercepts, is we set a function to 0, right? So if we're doing that to find x-intercepts, why not go in reverse and say, hey, a function that looks like this would have those x-intercepts. Now, I told you a couple things about it. Number one, we're going to deal with the multiplicity. Number two, I said I need to talk about this a little bit. And number three, we're going to put an A out front because we haven't been given a specific point to have a specific or unique polynomial here. We have a family of curves. So any A out front, any coefficient out front, positive or negative, doesn't matter, you would have exactly the same x-intercepts. We also have to match the degree. So the degree is important because otherwise we could add on any irreducible quadratic and still not have altered those x-intercepts. However, it is important for us to understand what that multiplicity does as far as a bounce. Hopefully you remember this, that an even multiplicity will bounce or touch and an odd will cross at those x-intercepts. It's really important for graphing. So let's go very carefully and make sure that we have this correct. So we know that the x plus 2 factor has a multiplicity of 2. So I'm going to work myself down. X plus 2 has a multiplicity 2. So I write my exponent of 2. X minus 5, so that's our x-intercept of 5. The x minus 5 factor has a multiplicity of 1. I'm not going to write anything right there. I don't need to. The 0, the x equals 0, x-intercept, the factor of x has a multiplicity of 3. And the 1/2, x equals 1/2, also has a multiplicity of 3. We can fake distribute in our head. Just a really easy way to find a leading term is to take your factors and your coefficient that have x's in them and multiply the largest power that you would get if you were to distribute. So x to the third, x squared, x, and x to the third. So x to the third, 5, 6, 7, 8, 9. So we know that our degree matches here. So if you were to distribute this, you would have an ax to the 9th as your leading term. That 9th power would be the largest one you could possibly get if you were to distribute this, and that matches with that degree. And that's how we would check our work. So here's the last thing I want to say. This factor can look different. I need you to hang on for this because people get kind of weirded out when you get to like synthetic division, and then you have fractions floating around. You go, wait a minute, I thought my factor was 2x minus 1. Yeah, it is. It's also x minus 1/2 because that's the same. There are two ways to go about getting that factor. Let me show you on that side. Another way that you could get that factor is by undoing that fraction rather than subtracting it. If you multiply both sides by 2, you would get 2x equals 1. And if you subtract 1, you would get 2x minus 1 equals 0. You go, well, which one's better? Depends on the case. It doesn't really matter, but what I'm trying to tell you is that the factor of x minus 1/2 and the factor of 2x minus 1 are identical. Set them both equal to 0 and solve it, and you're going to get positive 1/2 as your x-intercept. So whichever one you want to use is fine, but I will tell you that for synthetic division, that doesn't work. And this one would. If you needed to divide a polynomial by a factor, you wouldn't really want the 2 there. If you did, you'd have to do long division of polynomials, which isn't a huge headache. I'm going to show you both ways anyway. But I just want to make you aware of that so that when you get there, you're like, why the minus 1/2? Like, why do we need that for synthetic division? It's because you can't have an a that's not 1. Or, well, let's say that a coefficient of x that's not 1. So that's about it. So we're taking x-intercepts, we're finding factors by making 0 on one side, using the zero product property in reverse, and then making a function out of it. Understanding one thing, man, you need to get it, that if you do not have a specific point that's off of the x-axis, like a y-intercept or something like that, that you cannot say that this is the only function. It's a one of many, all of whom with a different coefficient would give you the same x-intercepts. Make sure your degree matches what they're telling you, so you're not allowed to multiply, have any factors, add a factor of irreducible quadratics. That would not change your x-intercepts. It would just make your function much more complicated. By the way, this, I think I gave you x squared plus 9. Keep in mind that x squared minus 9 is not an irreducible quadratic. You could factor that. It would give you additional x-intercepts. So that's certainly not allowed. The degree allows you, kind of prevents you from multiplying by any irreducible quadratics. So we're going to come right back. We're going to have some Kind of the same idea, but using graphs, and I'll show you how you can find a specific polynomial if you do have a point that's off of your x-axis. Okay, now that we have an idea of what to do when we're given x-intercepts, we can use them to find factors, use zero product property, create some sort of a polynomial where we normally should be distributing, but that is a family of curves that has the same x-intercepts and matches the degree that we're given. Now we're going to do that from graphs. It's a very similar idea, but the multiplicity is not expressly given to you. You have to read the graph. Also, a lot of times we can find a point that's not on the x-axis to make it so that we can find a specific polynomial and not a general one. So basically we solve for the a. I'm going to show you how to do that in the last two examples. So let's take a look at it. If we're able to find x-intercepts, then we can find factors, and then we can find a polynomial that has those x-intercepts that would match our graph. Now, we can't match our graph exactly unless we know a point that's not on the x-axis. That doesn't give it to us. So typically we're looking for a y-intercept or something that they've marked and said, hey, this is the point 1, -8. Well, our y-intercept here is 0. That's not going to help us because that's on the x-axis. To give it the shape that we need to match, you'd have to have a point that's not on the x-axis. One that's on the x-axis, you can sort of stretch this graph out and you wouldn't change that x-axis at all, and that's why we need one off of it. So here's the thought process. What we're going to be doing is we're going to say, okay, what are our x-intercepts? How is our graph behaving on them? Are we crossing or are we bouncing or touching? That's going to determine multiplicity. We're going to pick 1 for a cross. We're going to pick multiplicity 2 for a bounce or a touch. Could we pick 4 or 6? Yes, we could, but we're trying to keep it easy. We're trying to create a function that has that x-intercept that's not like, let's pick x minus 1 to the 7th power because it's odd and I know it crosses. You could do that. Probably it's not going to match that graph a whole lot because when you start getting very large exponents, you get super dynamic, super crazy graphs. I haven't even given you any markings on the y-axis because this is a sketch, but we're going to pick very easy numbers to work with, 1 or 2 for a multiplicity for odd and even respectively. So let's go through it. Our x-intercepts, if we look, an x-intercept is where our graph interacts with the x-axis. It intersects it. So either it crosses it or it bounces off of it. Our x's here are 0, 1, and 2. And right now, at this point, you are exactly where we were if they were to just give you zeros or x-intercepts or roots. We go, all right, well, you know what? We know that these x-intercepts, they have to come from factors. And those factors would be set equal to 0 if we were using the zero product property. Now that we have those set equal to 0, we can use zero product property in reverse and say, hey, our factors would be x and x minus 1 and x minus 2. And our function would have this as its basic form. Now, a couple things about it. Could you start adding in or multiplying some other like irreducible polynomials? You could, irreducible quadratics here. You could, except for the fact that our turning points really suggest that we have a degree 3. So there's 2 turning points. Remember that the number of turning points, maximum turning points, is 1 less than the degree. So probably this is a degree 3 polynomial. It has 1, 2 turning points, local maxima or local minima, and that's what we're looking for. This is probably a degree 3. So we're not going to be putting any strange factors in there. We're going to keep it simple. Also, we know that this was crossing, crossing, and crossing. So those factors should have odd exponents. Now we could do something like x to the 3rd and x minus 1 to the 7th and x minus 2 to the 711th. But why? I mean, if you wanted to be fun about it, I guess you could do that. But we're not going to be doing that. We're going to be keeping it simple, saying, hey, if we have a crossing x-intercept, so where the graph crosses the x-axis at the x-intercept, then we need an odd power. Otherwise, you'd have this idea of being even in the neighborhood or sort of even. At least you'd have the same sign in the neighborhood of that that x-intercept. Here we have different signs. So we're crossing, right? One's negative, one's positive on that, in that neighborhood around that x-intercept. And so what we would have to have is an odd power to signify that. We studied that in a couple videos ago. So we're going to say, hey, that's crossing, let's leave this odd, choose 1. That's crossing, let's leave this odd, that's 1. That's crossing, leave this odd, that's 1. And so our function has to have an x factor, an x minus 1 factor, and an x minus 2 factor. Now, we are not given a point off of the x-axis, and so this is one of many polynomials that could look that way. As soon as we start altering our coefficient, which in this case is 1, as soon as we start altering that, we'd start getting not different x-intercepts, but a different shape. Maybe it's more dramatic, or maybe it's flatter, maybe it's, well, it shouldn't be reflected. That should be positive. Because otherwise, oh man, I hope you get this. This is important. Right now, if you distributed this, you would have x to the 3rd power as your leading term. That end behavior would fit this. If I start putting a negative in front, that would be reflected. I hope that makes sense to you. Our end behavior here actually fits that. So we would probably leave it this way, or at least say that that has to be a positive coefficient in the front. Without a point off of the x-axis, you don't know for sure, but we're going to leave it just like that. If you have to distribute it to get the polynomial, you would distribute these two first and then run the x through it on distribution. Let's move on to the next one. So this is a little bit different in that we actually do have a point that's off of the x-axis. We are going to be able to solve for the a here. So in most cases, you have an a and you go, yeah, that could be any number here, not negative. Any number, and it would fit there. That's true. Now when we get this, we're not going to have that. So here's the way to start these. Number 1, what we're going to do is we're going to identify our x-intercepts. So x equals -1, and x equals 1, and x equals 2. We're also going to identify a point off of the x-axis if we can. This guy didn't have any, but this has the point 0, -1. Now, we go through the same process. We go, all right, well, if x equals -1, then x plus 1 has to be a factor, and x minus 1 has to be a factor, and x minus 2 has to be a factor of some polynomial. Also, we're going to look at this. This is probably a degree, oh man, really follow me on this one. This is probably a degree 3. Why? It has 1, 2 turning points. It ends in a sort of an opposite infinities idea. It's not ending like this or like this. It's ending like this. Its end behaviors like that. That has to be an odd degree. If you're opposite infinities, if you will, that's an odd degree. Why is it 3 and not 5? It only has 2 turning points. 5 most of the time is another turning point in there somewhere, another 2 turning points in there somewhere. So this is probably a degree 3. Think through this. Use that critical thinking head that I know you have. This is probably a degree 3. It probably has a negative degree 3. Otherwise, it would have looked like this, like that one. So this is probably a negative in front of a degree 3 polynomial. Keep that in your head. So when we solve this, if we don't have a negative in front of our factors, we've probably done something wrong. It has to mesh with this. It's got to be that. So we go, all right, here's our x-intercepts, -1, 1, and 2. Cool, find some factors. X plus 1, x minus 1, x minus 2. Let's build our polynomial. So f of x would have 3 factors in it. X plus 1, x minus 1, and x minus 2. Now is where we look for how that graph is intersecting the x-axis. Is it bouncing, is it or touching, or is it crossing? So we have a cross, we leave this a power 1. A cross, leave this a power 1, and a cross, leave that a power 1. So we're picking odd powers because crossing x-intercepts have to have a multiplicity that is odd. We're picking 1 so that we're making it easier. We don't want to pick 3 or 7 or 5 if we don't have to. And we already determined that we should have a degree 3. Why? Because it looks like a degree 3. I mean, it's a horrible way to say that. But it has 2 turning points. Probably it's going to be a degree 3. It has the end behavior of a degree 3. And so we're going to leave this as 1, 2, 3 factors that have x's in it. That's the most number of factors you can have for degree 3. Now, how in the world do we use the point that's off of the x-axis to find a specific function? Well, you'd give it an a. You'd say there's lots of polynomials that can have these three x-intercepts. That's true. There's lots of polynomials that can interact with across, across, and across. That's also true. There's lots of degree 3 polynomials that can look exactly like that, except for that point. That point makes a specific graph. So if you have x-intercepts and one point off of the x-axis, you can find a specific polynomial. And here's how to do it. Go through the same process we just did. Here's your x-intercepts, here's your factors. Okay, they're all crosses, so make them odd exponents. Let's choose one. Give yourself an A saying lots of different polynomials. But now, if this is your x coordinate, and this is your f of x coordinate. Your y coordinate, sure, but I'm going to use f of x because that's the output that we're talking about here. If that's the case, then you can fill out all of your x's with, well, in this case, 0. You can fill out your f of x with -1, and it will allow you to solve for your a. So let's try that. If I fill out my x's, I'm going to leave my a. My x should be 0. And my a should be, my f of x should be -1. Let's simplify that. Let's see, that's 1, -1, and -2. If we multiply this together, that's +2. So 1 times -1 times -2 is 2. Times a. If we divide by 2, oh my gosh, hey, we solved a. Now, all we need to do is say, hey, that a that we didn't know before, now that we've used a piece of information about a point that's off the x-axis, we don't have a general polynomial. We don't have a family of curves anymore. We have one specific curve. All you need is one point off of that x-axis to determine a specific curve that would have those x-intercepts. At least a degree 3. So now we say, hey, we know the a. The a is -1/2. Then we'd have those 3 factors. And that's about it. I hope that you understand that although this is not like super brain-bustingly hard math to do once you understand it, but getting to understand it will absolutely very much help you when you start graphing things in calculus. So getting the idea of, oh, that's what x-intercepts do. Oh, that's how multiplicity affects the exponent of the factor. Oh, wait a minute, a point off of the x-axis will let me solve for that unknown coefficient. That's huge. I mean, that's really, really, really helpful. Also, understanding beforehand what's going to happen, that's why I have you do those things, so that you can predict what's going to happen and check your work. We said, that's probably a degree 3. Why? Because that's 2 turning points. It's probably a degree 3. 1, 2, 3 factors. Hey, that's the most you can have. X times x times x is power 3. Hey, this end behavior looks odd, and it's a negative odd. Hey, there's a negative in front. If I distribute this, this would have -1/2 x to the third as a leading term. It fits the model. That's why we do these things, so that we can understand more appropriately how these graphs behave. Makes it much more powerful when we get to things like calculus. All right, and that, by the way, just for the last time, that's not a family of curves. This is one specific polynomial that would be that exact graph. So that's kind of neat to be able to find that. If you have to distribute again, you'd start here, distribute this. Once you simplify, distribute this. Once you simplify, then distribute the -1/2. And you'll see that leading term in there right away. It'll be -1/2 x to the third. All right, last one we're going to go through, and then we're going to be done. So how we start all the time if we're going from graphs to polynomial functions, how we know it's a polynomial, there's no weirdness here, there's no asymptotes, there's no gaps, there's no holes, there's no sharp points, no cusps. How we start this is by listing out our x-intercepts. So our x-intercepts are x equals -4, x equals -1, and x equals 3. We got one here, here, and there. Even though it doesn't cross, that's very important. That says, hey, that's an x-intercept. But wait, it doesn't cross. Oh, it bounces. Oh, what's that mean for multiplicity? You need to know that. Like, what does that mean when we cross versus when we bounce as far as our multiplicity? Because we're about to use it. So we have our x-intercepts, there's only 3, 1, 2, 3. We're gonna list any points that we find that are off of our x-axis. In our case, the y-intercept, I'm not exactly sure what that is. Don't guess at it. Find an actual point that is off of our x-axis. In this case, the y-intercept is not going to work for us. This, though, 1, -8, that's a great point. So we're going to be able to take our x-intercepts, build some factors, find a function, and put an a in front of it, and then use that point to solve for the a. So when we build our factors, we're going to have x plus 4 and x plus 1 and x minus 3 all equal to 0. We take care of the multiplicity in the next step. So we're going to start building our function. We're going to say, hey, by the zero product property, all of those 3 factors that are set equal to 0 would still equal 0 if I were to multiply them together. They'd have to by the zero product property. Now we're going to start taking care of our multiplicity. I didn't have to do the last 2 because we didn't have any bounces, but now we go ahead and we do that. So we're going to take a look at it and go, okay, look at our intercept, x equals -4. Look at whether this crosses or bounces. Sometimes we say the word touches. Well, this one crosses. So I know that x equals -4 is an odd multiplicity. So that factor has to have an odd exponent. We're going to choose 1. Now I check out the next x-intercept. X equals -1. This bounces or touches. This does not cross. So it bounces right off of that. So it is an x-intercept, but it has to have an even multiplicity. That means the exponent of the factor that we got from that has to be even. We're going to choose 2. So -1, here's our -1. Here's our factor from that x equals -1. That factor is a bouncy, and so it's got to have a 2. Could it be a 4? Possibly, but probably not. Why not? Well, how many turning points does this have? Turning points are local minimums or local maximums. So turning points are where we change from increasing to decreasing or decreasing to increasing. This has 1, 2, 3 turning points. Well, if it has 3 turning points, then 1 more than that is potentially our degree. So we say, all right, it has to have at least a degree 4, but it's probably not 6 or 8. Because it doesn't have more turning points. So we'd say the least degree this could have is 4. Why? Because degree is always at least 1 more than your turning points. Why isn't it 6? Well, because we don't have that many turning points. It's probably not that. Also, this isn't as dynamic. So, I mean, that'd be crazy. Or 8, that'd be super crazy. Why isn't it odd? Look at your end behavior. Look at your end behavior. Your end behavior says, I'm even. In fact, it says, I'm a positive even. Do you remember that? Odd, even, negative odd, negative even. So this is an end behavior that's a positive even function. So the reason why we don't have an odd the reason why we don't have odds here is because this right here would have to have a degree that is even. It has the end behavior for it. The reason why we're picking a 2 and not a 4 or something crazy is because our degree is probably 4. And if we start making a 4 here or 6 here, we're going to be blowing up that degree. Okay, last one. So x equals -3. I know that's a cross, so that's a crossy. So that means that this x-intercept gives us a factor that has an exponent that is odd. I'm going to pick 1. So we know that our function is based on the following factors. I'm giving myself an a so that I can solve for it. So I know I'm going to be able to find a specific polynomial, but I'm giving myself an a so that I allow an x and a y, or an f of x, and let me solve for something. So I don't know what that coefficient is yet. I know that it could be anything and have these x-intercepts, but it can't be anything and solve and be this exact graph. That's where the point comes in. Hopefully you're getting the point. One last time, just to make sure that you're with me before we wrap this thing up, so while I have your full attention, is that you should be thinking of what you're going to get before you do anything. You should be thinking, hey, I've got 1, 2, 3 x-intercepts. I'm gonna have a multiplicity 1 because it crosses, 2 because it bounces, 1 because it crosses. I should have a degree, probably 4, because it's even. It has to be 4 or 6 or 8. There's 3 turning points. I have to be at least 1 more than that, so 4, but it's probably not 6 or 8. We try to keep it as simple as possible and still fit our model. Now we're going to go ahead and plug in our 1 for our x and our -8 for our f of x, or our y. So that would give us 1 plus 4, 1 plus 2, and 1 minus 3. Of course, you don't want to forget about that square. So let's see, that's -40. Times -2 is -40. If we divide both sides by -40, we're going to get 1/5. You can also put 0.2, that's fine, it doesn't really matter. But we have gone ahead and we've solved this polynomial function. We know exactly what it is now, not a guess, not a family of curves. Because we have the point off the x-axis, we know that this function is 1/5 or 0.2 x plus 4 x plus 1 squared, and x minus 3. Let's see if it meshes with what we thought it was going to be. We thought it was going to be a degree 4. Is it a degree 4? 1, this would be x squared, so 2, 3, 4. That would be x times x squared times x, that's a degree 4. 1/5 is positive, so 1/5 x to the 4th would be your leading term. Do your fake distribution, 1/5 x to the 4th, or 0.2 x to the 4th. Positive x, so positive, that's 1/5 x to the 4th. That's even. That's positive even. That's a degree 4, should have at most 3 turning points, 1, 2, 3. It has our x-intercepts, -4, -1, and 3. That's a crossy, a bouncy, and a crossy. Here's a crossy, bouncy, crossy. It works. Has the point 1, -8 in it, so we know right now that this is the exact function that would have this picture to it. If you have to distribute, it gets kind of nasty. How you would do this, take care of your exponents that are not 1 first. So you do x plus 1 times x plus 1, distribute. Then distribute your linear factors over that, and finally distribute your coefficient, that 1/5. So I hope that makes sense. I hope now you really, really understand how multiplicity is used to create functions, how we can find a specific function if we have a point off of the x-axis, and if not, we cannot do that. So I know we've gone very, very deep into this concept. The reason why we do that, I'm not trying to teach you just how to do this stuff. I'm trying to teach you why it works and how you're going to use it in the future. Because if I can build that in there, if you understand why it works, man, it makes your life so much easier when you actually get to calculus to use this stuff. So I hope you're doing well. I hope this is making sense and working for you. And we will see you in another video when we start sketching from scratch on some of these polynomials. Have a good day.